Hi, in 10.1, there's 3 objectives: identifying characteristics of circles, recognizing chords and diameters, and recognizing the special relationships between radii and chords. So by definition, a circle has a center point, and the circle itself is the set of all points that are equidistant from that center. The radius is the distance from the center to the circle. We can have concentric circles, which are circles that have the same center and on the same plane. If two circles are congruent, then they have congruent radii. I think we learned that in chapter 3. And then a point is on the interior of the circle or the exterior of the circle. Point C is on the exterior, A is on the interior, O is also on the interior, but it's the center, and then B is on the circle. A chord is the connection of any 2 points on the circle the segment lies inside the circle itself. A diameter is a special chord because it goes through the center of the circle. These are formulas that we've seen already, and we need to remember them, so they're being refreshed here. The area is pi times the radius squared. Remember, area measures 2 dimensions, so it's squared. Circumference is like the perimeter. It's just a length. So it's 1 dimension, so the exponent is 1. Circumference equals pi times the diameter. These are some of the axioms that you're going to need to remember. If the radius is perpendicular to a chord, then it bisects the chord. If a radius bisects the chord, that is not a diameter, then it's perpendicular to the chord. You have to say that's not a diameter, because otherwise you wouldn't have a radius going through it. And the perpendicular bisector of a chord passes through the center of the chord. Let's look at some examples. In this first example, we're given a circle with a radius of 12 inches. That means the diameter would be equal to 2 radii, or 24 inches. To find the exact circumference, remember that the circumference is the diameter times pi, so the exact circumference here is 24 pi. When you type that into Moodle, you're going to need to type the 24 asterisks pi, open parentheses, close parentheses. Remember that we are using the Microsoft Excel notation. To estimate the circumference to the nearest tenth, we will want to enter that into our calculator. So 24 times pi gives us 75.39. Now remember, to the nearest tenth is 1 decimal place. So we have to look at that second decimal place. If that is 5 or more, we want to round up. So we would say it's 75.4. If you're not using the graphing calculator, that's fine. You can estimate pi as 3.14. And again, you would have to round up to 75.4. To find the exact area, you're going to need the radius squared times pi. The radius is 12. 12 squared is 144. Remember, that's 144 asterisk pi, open parentheses, close, on Moodle. To estimate the area, we would say it's 452.4. On this example, we're given a diameter of 6. Remember that the diameter is equal to 2 radii, therefore the radius is equal to 3. To find the exact circumference, that's the diameter times pi, or in this case, 6 pi. The estimate rounded is going to be 18.8 because the 4 is not 5 or greater. To find the exact area, the radius is 3, so when we square 3, we get 9. To estimate that to the nearest tenth, we would say we would have to round up because 7 is greater than 5, 28.3. Let's take a moment to briefly review the special right triangles. We had 4 Pythagorean triples that we were supposed to remember. And then we had the 2 special families, 30, 60, 90, x, x square root 3, and 2x. And then we also had the 45, 45, 90, x, x, x square root 2. I'm given AB is 10. The distance from A to BC is 8. Distance is always measured on the perpendicular, so I want to draw that in at a right angle. That distance is 8. I need to find that measure there. So I have an x, 8, 10. Can I factor anything out of that? Do you remember your Pythagorean triples? So x is 6, 2 times 3. And if that is 6, if a radius is drawn perpendicular to a chord, then it bisects the chord. So then the distance from C to B would be 12. In the next example, they tell us that CB is 14. ABC is 45. Find the distance from the center to the chord. Well, if that's 45, then this is an isosceles right triangle. If a radius is drawn perpendicular to a chord, it bisects the chord. So then that distance is also 7. Here we're given that angle ABC is 30 degrees and that the chord is 3 units from the center of the circle. Find the length of the chord. So here I have a 30, 60, 90 triangle that's in a ratio of x, x root 3, and 2x. Across from the 30 degree is 3. So I'm going to write the 3 there. I need to know the measure across from the 60 degree angle. So that's going to be 3 times the square root of 3. And if a radius is perpendicular to a chord, then it bisects the chord. So each of those parts is 3 root 3, which means the whole chord is 6 square root 3. When you enter that in Moodle, you're going to type 6 asterisk SQRT open parentheses 3 close parentheses. In our next example, we'll have to draw our own diagram. Find the length of a chord that is 15 units from the center of the circle. With a radius of 17. That's another Pythagorean triple. So that part is 8. And if the radius is drawn perpendicular to a chord, then it bisects the chord, so the distance we're looking for is 16. Find the radius of a circle if a 32 centimeter chord is 12 from the center. So that's 12. That whole distance is 32. If a radius is drawn perpendicular to a chord, it bisects it. So I have a 12, 16, and the radius that I need. If I factor a 4 out, my radius is 20. Two circles intersect and have a common chord that is 24 centimeters long. This is the common chord. The centers are 21 centimeters apart. The radius of one circle, it doesn't tell me which one, and I didn't get a diagram, so I'll just choose. That's 13. These are actually perpendicular, and if this whole common chord is 24, if a radius is drawn perpendicular to a chord, it bisects that chord. That's a Pythagorean triple, 5, 12, 13, from there to there. The centers of the circle are 21 apart, so this whole distance here is 21. This distance here is 5. That makes this distance here 16. So now I have a 12, 16, my other radius. Can factor out a 3 there, or sorry, a 4. My radius of the other circle is 20. In our last example, P just touches or is tangent to the y-axis, so it touches in only one place. The coordinates for P are -17, 20. To find the radius of P, we need the distance from P to the axis. So that would be 17, the same as that down there. To find PQ, we're going to use the distance formula, or we could use the Pythagorean theorem. If I'm dropping down a vertical and a horizontal, P is -17, 20. Q is -29, 29, which means if I'm at -17 and I walk over to -29, that's 12. If I'm at 20 and I walk up to 29, that's 9. Well, isn't that 3 times 3? And this is 3 times 4. So this is going to be 3 times 5, or 15. In the last problem, I'm going to erase those two lines. I now know that this distance is 15. This distance is 15. And from the first part of this problem, I know this distance is 20. And if a radius bisects the chord, it's perpendicular to the chord. So now I have right triangle AQP, where Q is the right angle. So this side is 3 times 5, or 15. This side is 4 times 5, or 20. Now be careful, because the trick is that some people want to say this is AQ is 5 times 5, but that's a leg. If this were 5 times 5, it would be 25. The hypotenuse always has to be the longest side. So this is not a Pythagorean triple. We can still use the reduced triangle principle. So I have 15 AQ 20, and I can factor a 5 out of that, and I have 3 unknown 4, and then use the Pythagorean theorem on the simplified or the reduced triangle. 3 squared plus x squared equals 4 squared. So x squared is 16 minus 9, which makes x the square root of 7, which then makes AQ 5 times the square root of 7, and AQ is half of AB, so AB is 10 square root of 7.